Each node in the recursion tree represents a recursive call. The upper half here shows the input size of this recursive call. The lower half shows the non-recursive work, the total number of basic operations performed by this recursive call. The number of branches indicate the total number of recursive calls that performed from this recursive call. And we take this number from this tree. Now, how do we analyze this recursion tree? We analyze it using depth level of recursive calls. Notice that the root of this tree is at depth level 0. The nodes at the next level are at depth level 1. We use the same definition for depth level here as we used for depth of a node in a tree. The depth of the node in the tree is equal to the number of edges from the root to that node. Next, we would like to calculate at each level how many there are nodes at each level. At the 0th level, we have 1 node. At the first level, we have 3 nodes. At the next level, each of these nodes will make 3 recursive calls, so it will be 9 nodes at the next second level. We notice some pattern. 1 can be written as 3 to the 0, 3 as 3 to the 1, 9 as 3 to the 2. So we would guess that at the last level, which is level H, we will have 3 to the H nodes at this level. What about input size? Input size at this 0th level is n, at the next level is n over 3, at the next level is n over 3 to the power of 2. So we suspect that at the last level we will have input size n over 3 to the power of h. And we also know that recursion stops when input size is equal to 1. So n over 3 to the h is also equal to 1. Next, we would like to count the total number of basic operations performed at each level. At level of 0, we have n operation. At the level 1, each node has n over 3 operations, and because there are 3 nodes at level 1, we need to multiply n over 3, multiply by 3, it will give us n total basic operations at this level. At the level 2, we have n over 3 squared total basic operations, and we also have 3 squared total nodes at this level. We multiply these two, we'll receive n total basic operations we have at level 2. The same pattern can be applied to the last level. At level h, we will have n total basic operations. Because there are n nodes, and when n input is 1, we have only one basic operation, then n times 1 is also n. So what is the running time of the algorithm? First of all, to answer this question, we need to know the height of this tree. From this input size of a node at the last level, we can calculate the total height of this tree. Because in the last level, input size is 1, and it is also equal n over 3 to the h. From here, we can multiply this equation by 3 to the h. Both sides of this equation will obtain 3 to the h is equal to n. Take log base 3 of both sides of this equation. You will have, on one side, you will have log base 3 of 3 to the h, and on the other side, you will have log base 3 of n. The left-hand side is equal to h, because it is base 3, and here we have 3 to the h, so this is equal to h, and it is equal log base 3 of n. This is the height of the tree. Now, what is the running time of the algorithm? It is the total number of basic operations executed during the execution of these algorithms. The total of n basic operations at each level, the total of log base 3 of n levels, and that means that total basic operations performed during the execution of this algorithm is equal to the product of the number of basic operations per level and the total number of levels. That means it is equal to n log base 3 of n. The running time is equal to n log base 3 of n, which can be expressed as big O of n log of n.